Hello YouTubers and fellow hams. Well, this is part 3 in my series on my 630 meter transmitter. I'm sitting here at the computer, so pardon the webcam video. I know it's not the best, but it is what it is. So I wanted to give you a progress update, and I wanted to show you the software and tell you where we're at on the hardware. I've got some good news and bad news. And the bad news is not terribly bad. It's just a delay, but we'll get to that. So first off, the software. I spent the better part of a day working on the software, and I've got it pretty much done, and it's working great. And so I'm going to show you the software in a flowchart. We'll talk about it briefly, and then I'm going to show you a demo of how well it's working, and it's working very well. That part of the transmitter is great. No problems at all. So let's look at a flowchart of the software. Now, the software is written in 3 sections. Okay, we've got on the left here the main program itself. In this middle section here, what we're looking at is a function that does the tuning. And this section over on the right is an interrupt routine. Now, an interrupt routine is a part of a program that is tied to a hardware timer within the processor itself. Okay, so let's say you've got a linear program that's running down. All right. If you had something that had to happen with precise timing every so many times per second, right? In my case, 1,000 times a second, I want to decrement a counter, and I'm going to use that for a timeout tail. You know how when you press down on the key, you switch into transmit mode, you send your Morse code, and then you release the key. The machine has to switch back into receive after a certain delay. That's the tail. And what I'm doing is I need a precise way of timing that tail. And a real easy way to do it is with an interrupt routine. So what happens with an interrupt routine is you set up a timer within the processor. Every so many clock ticks or every so many seconds or whatever, generate an interrupt. And an interrupt does kind of what it sounds like it does. It interrupts the processor. Whatever it's doing, it interrupts it, tells it to store its current state, and then go run this code. So I set up an interrupt routine for every 1,000th of a second. So 1,000 times a second, no matter what's happening, no matter what part of the program is running, the processor is going to put that aside, come over and run this routine, and then go back to what it was doing. So that's what an interrupt routine is, and they're very handy, like in an Arduino, because they can be so precise. If you need to count something exactly, that's one way you can do it. Another way you could do it is using the time function and doing some math. Read the current time and then check to see if you are so many ticks beyond the current time. And that works as well. But I like using an interrupt routine because I know that routine is going to run 1,000 times a second no matter what. So then I can easily, if I want to wait a half a second, that's 500, right? 500 times through that routine would be half a second. So that's what an interrupt routine is, and I use it for exactly that, for a counter for the tail when you let up on the key and you're done transmitting. All right, back to the program. So let's look from the beginning here. Okay, program start. The first thing that we do is we define everything and set up everything. We have to define the variables we're going to use. We have to set up the I/O ports and put them in the initial state that we want. We want the relays off in the transmitter, so we have to set those ports to low. And then I set up the interrupt routine, and then I have to initialize the SI5351 board to what I want its initial state to be. The VFO output's off, some default frequency set, and so on. And then we begin the main loop of the program. Oops. Learn how to navigate in this image viewer. And the first thing that we do is we read the spot button. Now I'm using spot tuning on this transmitter, and you'll see that it works pretty well. Meaning you're only tuning the transmit frequency when you want to. You push the spot button, and then you can tune it. And when you push the spot button, It sends from the second output on that SI5351 board, it sends some signal out the receive connector. So when you press that spot button, you'll hear your current frequency in your receiver, and that's how you'll tune the transmitter. Now that would be inconvenient if we had a very large band that we're working with, but remember 630 meters is only 7 kilohertz wide. It's not very wide, so we've got a very small area to tune over. So this works fine for that. So we read the spot button. Is it pressed? Yes, it's pressed. We call a tuning function which reads the tuning knob. We set the second VFO output and enable or disable it as needed. You know, if we just pressed in the spot button, have we just released the spot button? Do we turn that VFO on or off? Those decisions are made. And then we move on to the next part of the key program. If the spot button was not pressed, we just skip that whole tuning function. And that makes the program more efficient. It'll run quicker through this loop if it doesn't have to do this input-output every time that it runs through the loop, if it doesn't have to read the tuning control every time. The other reason that I did not want to read the tuning control every time through the loop is jitter. When you read a potentiometer with an Arduino, you get a value back from 0 to 1024 to cover the voltage range of 0 to 5 volts. But that value is not going to be precise. It's going to jitter up and down a few digits. And that's just due to the precision of the A to D converter that's reading in that voltage from the pot. You know, instead of getting a solid like 760, you'll get 760, then you'll get 764, then you'll get 757, and then you'll get 759, and then you'll get 761. On each consecutive read, it will vary slightly. And I didn't want the carrier that I'm outputting to be varying slightly, right? That little bit of jitter would sound bad if you're transmitting. So I only read the tuning when I'm pressing the spot button. And then once I'm not pressing the spot button, we stay locked on a specific frequency. So that's why this routine that's what's going on here. So is the spot button pressed? No. We go on and we do our keying, read the key input, and then we process keying. I use some flags and things. This loop is running through as fast as the Arduino can do it, right? So it's running through over and over and over and over again. It's not linear in the sense of like if in an old basic program where you would do step 1, do step 2, do step 3 and maybe wait for a little while and then do step 4 and continue on through the program. This is a loop that's running over and over and over again. So when you're doing something that takes time, like for example, we're pressing the key down to send a dot or a dit. You know, if you say dit and da, or if you say dot and dash, whatever, you know what I'm talking about. And you release that, that's an event that takes place over time, right? Well, over the course of the time that you're pushing that down and releasing it, this loop might run through 100 or 200 times. So I use flags to keep track of what I'm doing within the loop. It's complicated, but basically that's what I do. I read the key input, and then have we already processed setting the key down? We have. Then don't go through the whole rigmarole of setting the VFO again. You know, only do that when we first put it down. There's a lot of logic like that I had to work out, but it works. It works great. So anyway, that whole thing is one. I just put it in one big block in the flowchart here. Process keying, turn the first VFO on or off as needed, set the timeout variable, the tail, and flags as needed, so on. And then we just repeat the main loop. So this loop, this main loop here, and you can sort of see it all in the one area of the window now. From the top here to the bottom, this runs over and over again just as fast as the Arduino can run it. And that might be somewhere in the range of 100, 200 times per second. So it's plenty fast for keying. You're not going to drop any dits, and you're not going to miss the initial dot when you first push the key down. The other two parts of the program over here, the tuning function that's called when you push the spot button, it reads the tuning knob, it does some math to convert the value into a frequency range that matches the 630 meter band, and sets a variable to that frequency and sets the tuning. So I put that in a separate function so that I could only call it as needed. I could only call it when I press the spot button and not have to be reading the input output and jittering the frequency. And then the interrupt routine is really simple. It runs 1,000 times a second, and that's set. It's absolutely running 1,000 times a second. So it just checks to see, are we currently counting down? Are we currently in a tail? No, we just return from the interrupt. Yes, we decrement the counter. So I've got a counter that sets the tail delay, and by default it's set to 1,000, which would then be 1 second because we're running through this routine 1,000 times a second. So when I set that variable at 1,000, I know that immediately it's going to start counting down over the next second until it reaches 0. So that's how I do my timing. The actual program code itself is here, and I've commented it liberally. Once this project is done, I will make this all public. I'll publish the code, the schematic, the STL files for the coil forms, and any other material that goes along with the project, so anybody will be able to build it. So this is what the program code looks like. This from here to here, we're just defining, we're including the libraries that we need. We're defining all the variables that we're going to use, because you do have to define the variables you're going to use. The setup routine here, we set up the I/O pins that we're going to use for input and output. The first things we do are the relays, and we turn them off. And then we set up the input lines that we're going to read the switches with. I'm reading on the switches, I'm grounding a line. So when you push in the spot button, you're grounding that input. When you press down on the key, you're grounding that input. I did that because the connectors are mounted on the front panel, so their shell is already at a ground potential. If I wanted to sense those pins by bringing it to 5 volts, I'd have to insulate those connectors. So I'm doing it by grounding. So that's what we're doing here. We're setting up the pins. Digital write, setting a pin high here is just enabling the internal pull-up resistor, so the pin's default state is at 5 volts, and then when we ground it, that'll be our input. So that's what we're doing there. This is initializing the SI5351 board here, and setting its initial frequency and turning its outputs off. And then this sets up the interrupt routine. That's just setting up a timer within the Arduino. That's really complicated. I actually lifted some of that code from somebody else's project. I haven't dug into what exactly is going on there, but I know we're setting up a timer and we're giving it a value. And then here's the interrupt handler routine that uses that timer, and 1,000 times per second we do a simple if statement. If tail, which is my variable that my counter, is greater than 0, and we are not keyed down, we're not keyed, then we just decrement tail. So as long as we've released the key, we're not keyed, and the tail counter is greater than 0, we'll decrement it by 1. So that's simply changing that counter. That's all that's doing. Now here's the main loop. All right, this is where it all starts. The spot tuning routine is here, where we read the spot switch and we decide what we're going to do. If the spot button is pushed down, we call the read tuning function, so we read and adjust the frequency variable, and we set the VFO frequencies to our new frequency that we just read from tuning. So this little if loop here, as long as the spot button is down, it's reading the tuning knob and setting the frequencies of the VFOs. And then there's some logic here that turns the VFO on or off depending upon whether or not we just pushed in the spot button or whether or not we just released the spot button. That just turns that second VFO output on or off to our receiver. And then there's keying routines here. I'm not going to go through this because it's kind of complicated. I commented every line. You can follow the logic, but basically what it's doing is it's checking to see if we are in a delay, if we're in that tail, and if we still are, it does nothing. If we have left that tail, we've let the key up and we've left the tail, that we're past our timeout, it turns off the VFO output. So we're keying by turning the VFO output on and off. That's how we're keying. And then the power amplifier will receive that signal and amplify it and will transmit. So that's how we're doing the keying, just turning the VFO output on and off. It's very fast. That little clock generator can be turned on and off extremely fast, and it's very stable, so we don't get any chirp or key click. And then there's some logic here. Did we just key down or did we just unkey? And we make some decisions there and set the counter, set the tail delay, turn the VFO output on or off. So that's all the keying that happens there, and that's the end of the main loop. That's all we do in that main loop. This is the read tuning function that we call when we push the spot switch down. It does a little math. It reads the reads the value from the tuning knob. It compresses that into a range that matches the frequency range that we're setting. All right, so we're reading 0 through 1024. That's what we're getting back. I do a little math to convert that into a value from 0 to 7,000, because the band is 7 kilohertz wide. And then I just take 472,000, which would be the bottom of the band, right? 472 kilohertz, and I add that value onto it. So if the pot is at 0, we're adding 0 to it. We're right at the bottom of the band. If the pot is halfway up, then the math gives us an add value of 3.5 kilohertz, or 3,500, right? 3.5 kilohertz, and that gets added to 472 and puts us at 475.5 kilohertz, or whatever the middle of the band is, right? Well, anyway, that's the math. It does all the math right there, and it sets our frequency value to a variable, so that up here where we're setting frequency on the VFOs, we're setting them to the right frequency. So, yeah, that's the program. Like I said, it sounds pretty complicated, but hey, it works. And I'm going to give you a demo. I'm going to point the camera over here at the transmitter and at the Kenwood, and we'll give you a demo of how it works. But before I do that, let me talk about what's going on with the hardware. Okay, I wanted to use this little case. You know, I've shown you the case, and so I wanted to build things down, and I tried to build the power amplifier down onto a smaller board, kind of cramming everything together. That didn't work. I kind of expected it wouldn't, and I had a couple of thumbs down on the video, and it was probably from more seasoned guys that have built lots of transmitters or power amplifiers, and they just looked at my design and went, that's not going to work. Well, it didn't. Everything's too close together, and the PA just goes into oscillation as soon as you start sending it signal. The coils are interacting with each other. They're interacting with, or they're messing with the SI5351. It's just not going to work in that small case. So what I'm going to have to do is I'm going to have to rebuild the power amplifier, and I'm going to build it laid out kind of like the original designer did on a larger piece of PC board. I got to find a little bit bigger case, and I think I've got one that'll work. I'm going to rebuild the whole thing into the bigger case with things spaced out and isolated, and that should take care of that. The front end, the keying and the VFO, they're working perfect. The Arduino's plenty fast to handle the keying. There was some concerns about that in the previous video. Plenty fast. You do not drop the first dit at all, and it can keep up with you as fast as I can send. It could probably do 30, 40 words a minute. I mean, it's plenty fast. So that's working great. Keying is working great. The signal source is working great. I just have to get the power amplifier built properly and spaced out into a proper case. The other thing that I ran into when I first built the transmitter, well, here's a clip from down at the bench when I first powered it up and with the problems I first ran into. And then we'll come back and we'll do a demo. Well, here we are at the bench, still working on the transmitter. I made great progress yesterday. I pretty much completed the software, got that all done, and then I uncovered a couple of bugs, hardware bugs, or actually Moments of stupidity on my part. The relay drivers, I wired them wrong. The way to do a relay driver is B plus, or the 12 volts, into the relay coil to a collector on an NPN transistor like a 2N22222. Emitter to the ground, so the transistor is just a switch, and then your signal coming from the Arduino through a resistor like a 2.2K resistor to the base of the transistor. And the transistor becomes a switch, grounds the relay coil, and relay pulls in. And I wired them with the transistors on the high side of the relay coil for some reason. I don't know what I was thinking. I put 12 volts into the transistor to the coil to ground. The problem with doing that is that the coil of the relay is a resistor, and it has a voltage drop across it, so it effectively raises the transistor above ground, which then effectively raises the turn-on voltage on the base. So the signal coming from the Arduino was just barely turning the transistors on, and the relays weren't quite pulling in. So yeah, it's my fault completely. I don't know what I was thinking. I knew better. So I redid those with the transistor on the low side of the relay, and they're pulling in just fine. So I spent all day yesterday on the software, and it's working just beautifully. And I hooked it up to the dummy load, and I thought, well, let's see what kind of power we get out. And I hooked up the power to the PA, and I keyed down, and I'll show you the scope here in a moment. But yeah, nothing. We're drawing about 200 milliamps, which is some idle current on the MOSFET and the relays, and then the rest of the circuitry is drawn like 60 milliamps. The Arduino doesn't draw much. But we're not getting any RF out of the PA at all. So I've got the scope hooked up to the gate on the MOSFET, and I'll show you the scope. So here's the scope. I'm going to key down, and there's the signal on the gate of the MOSFET. And 3.9 volts peak to peak, but only 1.52 volts mean voltage. Yeah, not enough to turn on the MOSFET. The SI5351 doesn't put out enough drive. Duh, should have seen that coming. So I need a little buffer amplifier drive stage, which will just be a single NPN transistor. I'll throw a schematic up here, the basic idea. So yeah, I got to build that. I'm going to build that down on the VFO board, which, let me see, GoPro view. Yeah, you can see it in there. I'm going to use this empty space over here, and I'm going to put the driver there, and then bring a coax from that over to the PA to bring the signal over to it. So after I do that, we should have a transmitter. Okay, I have the transmitter hooked up to my external long wire, and I've got the receive output from the front of it going up to the Kenwood. I've got the Kenwood tuned to the 630 meter band. I'm going to move it up to, let's say, 467. Yeah, some kind of carrier in there. Yeah, we can go to 479, right? So we'll go 478. All right. So tuning. I'm interested in that frequency, 478. I need to tune the transmitter. We turn the volume up on the radio. I just hit the spot button, and we're tuned. Just that easy. As soon as I hit that spot button, it sends a signal out to the receiver only. And I could use that to spot another station as well. If I was tuned into somebody I wanted to answer, I could match their tone by doing that. Now that's not transmitting. It's not sending anything out RF-wise. It's not firing up the PA. It's only sending that to the receiver. So that's spot tuning. So now that we've tuned, and you can hear, remember I was talking about jitter? Listen to the tone. I don't know if you can hear that, but it wavers just slightly. And that's the Arduino. It's fiddling around with that value slightly. But once I release that button, it's locked in. And when I transmit, you can hear that it's nice and stable, nice and solid. So, how fast is it? Well, like I said, plenty fast. See, it's not going to drop any of that first element, and it'll keep up with keying just fine. I'm not going to try to send too fast because I get sloppy when I'm fast, but yeah, see, I get sloppy when I try to go too fast, standing up in front of the desk with my arm at the wrong angle, but you can see that it's plenty quick. And you can also hear the tail, which I currently have set at 1 second. Hear it click back into receive mode. So, yeah, the front end of the transmitter is working great. I just need to rebuild the power amplifier, and that'll be in the next video. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.